Computing pi? That's easy! For this year's Pi Day, I have computed pi in Minecraft, and this is how I did it. I've been holding off on this for a while now, partially because there's a really cool person that I wanted to work on this project with. Anyways, computing pi is really easy, but as an additional challenge, I personally want to make a pi computation that is both quick and accurate. So join me on my adventure to compute the most famous irrational number in mathematics. Before we go any further, fair warning, this video is going to be math heavy. That said, this is my first Pi Day video and I'm deliberately keeping the math as approachable as possible. No calculus, no black magic. If math really isn't your thing, here's a timestamp, feel free to jump straight to the final build. Starting our computation of pi, I would like to start with the Monte-Carlo approach. Yes, to all you math nerds, this isn't the fastest converging computation to find pi. Like I said, my first Pi Day video. I want to keep it simpler for the first time round. Monte-Carlo simulations are a broad class of algorithms based on repeated random sampling. In simple terms, generate a bunch of random numbers, check which ones satisfy some condition, and count them. In our case, we are finding the probability of having some random point fall within a circle. So let's start by just drawing a circle in some blocks, making sure that the circle takes up as much space as possible. Our formula for finding pi is counting the number of times some random point in our box lands within our circle, divided by the number of random points that we computed. But how? Well, to answer that, we need to look at our formula for finding the area of a circle and the area of our square. The formula for the area of a circle is a equals pi r squared, and the area for our square is a equals l squared, where l is the length. The key idea here is that when we generate random points, the fraction of points that land inside the circle approaches the fraction of the area that the circle occupies in the square. The more points we throw at it, the better of an estimation we can achieve. The reason why the fraction of random points approaches is that random events are random. So let's play a little game with dice. Roll a 6-sided dice. The probability of rolling each side of one dice is 1/6. We find this by counting the total number of events that are favorable. So if we wanted it to land on the one side, there is one event where it does land on it. Then we divide it by the total number of events that can occur, or the dice lands on sides 1 through 6. Now, as we roll more dice, for each given side, we can expect each face to appear 1/6 of the time. But since dice rolls are random, and the number of rolls are low, we can against like this fairly easily, breaking this 1/6 rule. But as we roll more and more dice, these random events even out, and for each face of the dice, we approach this 1/6 rule. In our case, with the fractions of the areas, we have random points that could be inside or outside the circle, and we could have a streak of points that favor one of those two, making our guess different than what we would expect. But as we sample more and more points, we would expect to see it approach our value for pi. So this ends up being pi equals inside divided by total times length squared divided by r squared, stemming from pi r squared equals l squared. Now here's a neat trick with this. Since the circle has an infinite amount of symmetry, we can just look at one quadrant. Let's do the positive and x section because that makes it the easiest since we can generate random points really easily in a square. This is also really powerful because it's the same as adding the point 4 times, so we can essentially do a quarter of the work for the same results. Since we have cut the area of our circle into a quarter, we just need to change our area for a circle to a equals pi r squared divided by 4, which makes our pi calculation pi equals 4 times inside over total times length squared divided by r squared. And that's not all. We have another little trick we can apply here. If we make our radius of the circle 1 and make sure the side length of our square is as small as it can be, or just 1, 2, our extra division here just disappears into a puff of 1 divided by 1. Now, what is really cool about this, we can also expand upon this into higher dimensions. I'm going to make a pretty large jump here since this isn't as relevant, but I thought it was pretty cool. So what we can do is take a generic formula for finding the volume of spheroids, or the higher dimensional spheres. V equals pi to the power of d over 2, divided by the gamma function of d over 2 plus 1, all multiplied by r to the power of d, and sub that in place of our circle area. Here d represents the dimension count. This weird thing is the Euler gamma function, and r is our radius. And our cuboid is v equals L to the power of d. Since we also want to stick in the positive real numbers, we also have to add this term here, 2 to the power of d, to find the fraction of the manifold that we are looking at. And as our last step, we need to normalize our equation, which brings us to our final equation of pi equals inside divided by total times 2 to the power of d times the gamma function of d over 2 plus 1, all raised to the power of 2 over d. I know, big jump. Again, this is more of my own interest to look at, but this equation does get us to our original equation that we looked at earlier. I will solve this part here for you, but I will leave it up to you to figure out if it really does get us back to our original formulation. Now, our formulation is great and all, but if you ever want a decent precision of pi, you need a lot of unique points. And that's fine if you have floating point numbers with near infinite precision compared to doing the same calculations with fixed point numbers. Although fixed point numbers do technically have greater precision, but in Minecraft land, our floating point numbers on our computers are much bigger, but I'm gonna kind of ignore that. To get a decent precision of pi using fixed point numbers, you need to have at least 16 bits for somewhat decent precision. But anything beyond 8 bits using the Monte-Carlo method would take years to compute. So knowing that we're going to be working with fixed point numbers and we have a finite search space, let's try optimizing our Monte-Carlo function to make our computation time as small as possible. Firstly, let's look at our random number function. Most notably, this fraction is assuming that we have infinite or humanly infinite floats of arbitrary precision in our space. But we don't have that. We have a 65,000 by 65,000 grid of points that we can compute. Now, how are we going to do that? Well, if randomness is slow, because, well, it's random, why don't we just remove randomness entirely? So how about we just check all of the points in the grid to get our fraction and just run the equation as normal? I mean, we could do that, but we run into the same issue. The search space is exactly the same as when we started. But the key difference here is that we have reframed the question so that we can apply some new algorithms to find our points. Let's start by just finding the y-coordinate for its quarter sphere using a given x location. So finding the distance to some point, let's start there. That's the Pythagorean theorem, a squared plus b squared equals c squared, where a is x, b is y, and c is our radius for our circle. So r squared equals x squared plus y squared. But we want y to be alone. Doing some algebra, we get y equals the square root of r squared minus x squared. Perfect! I don't really like that square root there. Square roots are really mean to compute, especially doing it quickly when you have to do a lot of them. I bet there's some method out there that at the very least draws circles that was made a long time ago when computers were not as fast as they are today. And you know what? Bresenham has just the algorithm I need. Man, that guy has done so many rendering things. He has a line algorithm and a circle algorithm. Wow. So to make sure this actually works, I'm going to quickly program this up and double check the answer. I'm not going to pretend that I know how and why these are the exact values being used, but generally, this function starts our circle drawing at the very top, and based on this decision parameter that generally gets updated to match the shape of the circle, plot the point. And that's not pi. Alright. I've come to conclude that as great as this algorithm is at drawing circles, it turns out it's horrible at getting perfectly circular radiuses. So this guess is way off. So what's going to happen instead? I'm going to spend some time implementing an algorithm of my own. So how my algorithm works. Starting at the largest position on the radius, on the x-axis, or right here, I'm going to do that same idea of y equals the square root of r squared minus x squared, but I can just check if the right-hand side is greater than the left-hand side, and decrement by x by 1. Compute the square and repeat until r squared minus s squared is less than y squared. It is at this point where I can add the number of points and increment y and compute y squared again. But you might also be noticing that I'm not actually multiplying anything anywhere. That's because I can use this handy formula. N squared equals the summation of 2i minus 1. This script is getting fairly long now, so I'm going to leave this as a proof for you, the viewer, to do, mainly because the proof is not relevant to this video. But what I can do is every time we end up needing to compute x squared or y squared, we are always decrementing or incrementing x or y. For y, I can just apply another iteration of our summation whenever we increment. And for x, since we're starting in a state where x squared is pre-computed before running, we can just remove the last iteration of our summation to make it x minus 1 squared. This way, I don't need to use a massive 16-bit multiplier when I can just use a small and quick 32-bit CCA. Okay, I'm gonna go build this thing now that we have a good algorithm. So I'll see you after the montage. During the build, when I was implementing these lines here, I found that I could get a better pipeline by making it x squared minus equals x times 2 minus 1, then decrement x. It does mean that at the very top, x equals r and y equals 0 becomes x equals r minus 1 and y still equals 0. To apply that first subtraction when applying the reset. And what I found really funny is that applying this change, it actually made my estimate for pi just a little bit better, going from 3.1416 to 3.14152, not accurate. I could also do the same optimization with the y squared term here. Here's another thing I managed to optimize a bit more. This line here, while y is less than or equal to r. If it is changed to y is less than or equal to x, we cut the search space in half. But since we have cut the search space in half, we need to double the count for each row that we're counting before. So that means we have to do x minus y plus 1.5. Basically, we count the full row, and then we knock off the stuff here that we have already counted for. Before that, x plus 1 was coming from here, where we decremented x, so it would be off by 1 every loop. So we need to add that back in, but it would still be off by 1 for every other iteration, so we need to add half a point every iteration. Now, since we're counting only one octant, we need to take this final multiplication and change it from a 4 to an 8, or multiply by 2. But we also introduce an issue with this implementation. Can you spot it? If not, it's right here. This. We can't add 0.5. That's because I would need to add an extra bit to the bottom of my adders, and I don't really want to do that. But there is a really easy fix. We can just multiply this whole statement by 2, so we get 2 times x minus y plus 3. But since we doubled this, we need to have our final multiplication, so that brings us back to a 4 instead of an 8. Handily enough, this also allows me to just entirely remove our checks if x is less than 0, since they're stopping at the midpoint between x and y, so x will never get low enough. Since my build is focused on just raw count of pixels, and I don't really feel like building the true Monte-Carlo method myself, I thought I would bring on Among Us PvP to talk about their build from last year's Pi Day. So, Among Us, tell me a bit about yourself.
Hi, I'm an Australian kid who used to be into Redstone from around 2021 to 2024. I used to run a YouTube channel called Among Us _PvP, but that's largely dead now due to my pursuit for final exams. Yeah, not much else to talk about there.
Oh, that's really cool. That's a shame you haven't been uploading recently. You have some really cool projects on your channel. So, in short, I have you on today to compare our two methods of trying to compute pi. You used your random number generator, Monte-Carlo method, and I used a deterministic pixel counting method. Tell me about your implementation.
I'd start my algorithm by basically running it on a constant loop, and within each loop, I'd calculate 2 random 7-bit binary numbers, right? Using the classic dropper, 1 out of 2 random chance kind of stuff. These binary numbers would correspond to coordinates on a big screen, and essentially I'd run the algorithm to check whether the coordinates were inside or outside the quarter circle, right? Then, depending on that, I would update 2 counters. So one of the counters was 16 bits in length, which is basically to account for all of the possible points being filled up, and the other one was also the same size. And then each loop took roughly 45 seconds. I wouldn't be able to pull it up right now, but it was quite a lot of time.
That sounds like it would take a really long time to run.
Yes, it did take around 15 hours of running at 250 redstone ticks per second using Carpet. This value is a little bit off, obviously, because my computer lagged quite a lot and a lot of the calculations just started stuttering and everything. But in general, I had to leave it running for quite a long time.
And how long was your clock cycle, or how long between each iteration?
Yeah, roughly 45 seconds.
Oh, wow. I can see why it took so long to run. Now, I would like to briefly talk about your precision of your estimation. Firstly, how happy are you with your results?
So, to be honest, when I was running this experiment, I was quite happy with my result, because I was relatively inexperienced with Redstone, and I didn't really know what to expect when I was running into this, because there was only one other person who had done this project at the time, and publicly released it to YouTube, obviously. But looking back on it, since the method is reliant on sampling a bunch of random points in a certain space, and I have a limited output space, obviously, only 7 bits by 7 bits, it means that it's difficult to make a good estimation, especially when you have limited time and you might not be covering every single point in the plan. So That means at the end of the day, running calculations, you'll have roughly only 65,000 points that you can reach, and obviously that limits the estimation. So at some point, obviously samples start repeating, and the estimate becomes less accurate. And overall, it can become quite inaccurate. Now, am I happy with the result that I got looking back on it now? I think I am, because I mean, given the constraints of what I was working with and how I decided to approach the problem, I'm quite happy with the fact that it managed to turn out this way. Could I have improved on it? Obviously, there are many ways you can improve on this result. For example, forcefully avoiding recalculation of the exact same point, or which would be similar to a deterministic pixel counting approach, or increasing the screen size, obviously. But in general, I'm quite happy with the result that we achieved today.
That's all really interesting. Thank you very much for being here and taking the time out of your busy day for this.
No problem.
So, it turns out, as amazing as counting random samples is, it takes a really long time and a lot of unique samples to get a really good estimation.
I'm still here, right?
Oh my god, that's right, I had people over. Anyways. So here's the real takeaway. The Monte-Carlo method is flexible, simple, and elegant, but it is also painfully slow to run in Minecraft. It is a bit more of a manageable pill to swallow when you have a system that can run billions of cycles per second. Pixel counting is fast, deterministic, and surprisingly easy to build once you get your functions and formulas correct. Here are my replay files actually building the thing, and the first hour or so was trying to just figure out what I screwed up with my CCA, which I historically already fixed. I just forgot, so I had to re-figure it out. It was the whole ordeal. And it really paid off. Looking at some of my testing when I got the thing working, it was managing to run at roughly 1,100 TPS, or 550 redstone ticks per second, which is about double that of which Among Us PvP's build could run at, and it ran in about 50 minutes, about 20 times faster than a 7-bit Monte-Carlo method. Look at that! Our result has an error of about 0.002%. Really cool. What I love most about this build is that it starts from the classical idea of trying to compute pi with Monte-Carlo, and there are some personal nostalgia points for me. One of my first introductions to algorithms was the Monte-Carlo method back in high school, so revisiting this but in Minecraft was just really cool for me to see. I'm going to leave this video off here, and I know I haven't reached peak computation, and frankly, the question is, how far can we push it? I don't know if I can commit to another Pi Day video for next year's Pi Day, but who knows? Maybe I'll get another Pi Day out by Christmas. Wow, wow. You froze because you were trying to figure out how to spell montage? What?